Hello, hello, hello. If you're watching this, you missed day 1 of our week 12 Foundations of Technology lecture. Let's go ahead and get started. So we're talking about mechanical advantage and efficiency, as well as simple machines this week. Got a lot to do. There are 2 assignments to be aware of. Assignment 20, mechanical advantage and efficiency, is due Wednesday the 18th, and then simple machines is going to be due Friday. Our objectives are that you can define and calculate mechanical efficiency, name and describe the functions of the 6 simple machines, and perform calculations using mechanical advantage associated with said machines. Let's go ahead and get started. To start with, let's take a look at efficiency, which is something we didn't quite get to last week fully. Efficiency is figuring out how much of the work that you're doing is being preserved inside the machine and output at the other side. So we can say that input work is equal to output work, or Wn equals output W out, in theory, right? Ideally. Keep in mind that work is force times distance on both sides here. So this is force in times force or distance in is equal to force out times distance out. However, some output in terms of your work is going to be lost due to friction. This is just an inevitable truth. You cannot get rid of friction. You can reduce it a little bit, but you can never be fully rid of it. So the comparison of work input to work output is called efficiency. No machine is 100% efficient, and we are going to be taking a look at how this works. So how efficient is a machine that takes 40 joules of work and produces 30 joules of work output? Well, a joule is the amount of work done by doing or providing 1 Newton worth of force over the distance of 1 meter. We have 40 of them going in, only 30 coming out. So what's the efficiency? Well, this is the formula. We take the work out divided by the work in and multiply by 100% to get the percentage. Remember, efficiency is a percentage, so that should be the symbol I see behind it. I should not see joules, I shouldn't see newtons, I shouldn't see meters. So in this case, 30 joules divided by 40 joules times 100 gives you 75%. So this machine is 75% effective. 25% of all of your total work is lost due to friction. So not the best maybe, but definitely possible example. Let's take a look at another example. Let's say you do 250,000 joules of work and your mower does 200 joules on the lawn. How much efficiency do you have? Well, 80%. Straightforward, I hope. Nothing too crazy. You're going to be dividing the smaller number by the larger number every time here. If for whatever reason your machine is giving more work out than you're putting in, it's a magical machine and it should not exist. The next topic is the 6 simple machines. So let's go ahead and get started. There's a lot to cover here. We have the inclined plane, the screw, the wedge, the lever, the pulley, and the wheel and axle. And we'll cover them in that order. These are things we've already looked at. Inclined plane is a really powerful machine, and it actually is the basis for several other simple machines. Inclined plane you can think of like a ramp, used all the way back in ancient Egyptian times, still around today. Anytime you have any kind of slant, you're looking at one. Now, how do we actually figure out how much mechanical advantage you have in an inclined plane? Well, remember that the work output is the input force times the distance, and the work output is the output force times the output distance. So in this particular case, if our output is 10 newtons times 3, that being the distance, we could find the force input by saying it's some kind of input times 15, right? Well, what number makes that equation balanced? It's 2. 10 times 3 is 15, 10 times 3 is 30. Some number times 15 is also 30. That number is 2. Now you can always do it this way and find the missing number inside this equation. You can also simplify a little bit here and say, all right, the total mechanical advantage we're going to be having is just the ratio of the long side of your ramp, the hypotenuse, to the height. So in this case, 15 divided by 3 gives you the mechanical advantage of 5. So for every pound of force I put into this machine, I get 5 pounds out. And that's simply the difference between these heights as a ratio. All right, let's keep going. With a screw, you have a similar idea. You can think of a screw as a really long inclined plane wrapped around a cylinder, like a spiral staircase, or more aptly, a spiral ramp. The mechanical advantage of a screw is calculated by dividing the circumference by the pitch. The pitch of the screw is how many treads you have per given distance. So whatever you're measuring your circumference in, that should be what you're measuring the pitch in. If you're measuring it in inches, then you can use inches for both. So this is again a ratio, and we'll take a look at some examples of this later on when we do our assignment. A wedge, any kind of sharp object is going to be your wedge. Hammers, knives, scissors, anything sharp. Wedges are used to split things apart. Wedges are composed of two inclined planes right next to each other. And by sticking those inclined planes into a surface, you're facilitating its splitting apart. The mechanical advantage can be calculated by taking the long side of your triangle. If this is your wedge, this is the pointy side. This is going to be the long side of my triangle, the sharp part, and dividing it by the thick end over here, this distance. So for example, if we assume that the length of this slope S is 10 and the thickness T is 4, the mechanical advantage of this particular wedge would be 10 divided by 4, or 2.5. The mechanical advantage is gained by using the wedge, requires a corresponding increase in distance. So keep in mind, none of this is free. Every time you use one of these machines, you're losing something, either distance or force, to gain something, either distance or force. In this particular case, you would be having to drive something a longer distance to get some kind of force advantage. Now, let's take a look at levers. Levers are very interesting because you have three different kinds. This is the first class lever. In a first class lever is probably what you're used to seeing. This is kind of like a seesaw. You have a load on one side, and you're going to apply an effort on the other side to lift it up. The way you figure out the mechanical advantage of this thing is you take the ratio of the distance from here to the effort, from the fulcrum to the effort, and you divide it by the distance from the fulcrum to the load, this distance. Nothing more to say here. Some common examples would be pliers, crowbars, seesaws, things we're fairly used to. Now here things get a little more interesting with the second class lever. In the second class lever, both the effort and the load are on the same side from the fulcrum. And the distance from here to here, divided by the distance from the fulcrum to the load, will give you the mechanical advantage of this thing. So a second class lever, you're always going to have a mechanical advantage greater than 1. Just by definition, this is a longer distance here than from here to here. Some examples include nutcrackers, wheelbarrows, doors, bottle openers. So in a nutcracker, you can think of this hinge at the end as being your fulcrum, the force you're applying on the handles, and your output is going to be the force on the nut. Obviously, the distance from the handle to your hand is going to be longer than the distance from the handle or from the hinge to the nut, and therefore you're going to be applying some greater force but having to move a greater distance here. Same thing with a wheelbarrow or any of these other examples. The last kind of lever would be a third class lever. In this particular case, our load is all the way on the end and our effort is closer to the fulcrum. By definition, these will have a mechanical advantage of less than 1, some positive number that's a decimal. So you might say, what's the point? Well, remember, anytime you have a mechanical advantage less than 1, you are going to have to use more force to use this machine, but you will get a distal advantage. So some examples that you might be interested in here are tweezers, hammers, shovels. Your arm, for instance, is a class 3 lever. But more importantly, catapults, which is something we'll be building, is going to use the same exact concept. We want something to be flung really far, so we're going to apply more force to the middle of our lever to create a really long lever arm that throws something really far. Next, let's look at pulleys. Pulleys are wheels and axles with a groove around the outside, and pulley needs a rope, chain, or belt around the groove to make it work. Now, pulleys only provide a mechanical advantage if they're not fixed. If they're just hanging there and the rope passes right through, this pulley does not move, there is no advantage to it. Now, it can be useful to redirect your force. Instead of lifting up, I could be pulling down, but it does not actually provide any mechanical advantage. A movable pulley, however, does provide mechanical advantage, and to calculate it, you need to count the number of ropes that support the movable pulley. So in this particular case, we have a hanging pulley here. It does not provide any advantage whatsoever. However, this sliding pulley has 2 ropes going into it, and therefore this is going to be a 1 to 2 system. The effort you need to lift the slope is half the weight of the load. It's a mechanical advantage of 2. And the main disadvantage is you'd have to pull twice as far on that rope to lift this object. Last but not least, we have wheel and axle. The axle is stuck rigidly to the large wheel, and then this is a fan contraption. You can also think of just a regular car wheel or bike wheel. In order to figure out the mechanical advantage of this contraption, you need to look at the difference between the radii of the axle in the center and the wheel at the rim. So in this particular example, this is 5 units and this is 1 unit, so this would be a 5 to 1 mechanical advantage system. You can use these in different ways. If you apply a force to the outside of this wheel, for instance, when you're driving a car, you're going to have to move the wheel much farther, but you're going to get a force advantage. If you drive the wheel at the axle, you're going to have to apply way, way, way more force, but your wheel is going to go quicker. So you're going to create a distance advantage. That sums up our lecture on simple machines. I hope you got something out of it, and I look forward to seeing you next time when we'll take a look at complex machines, which are going to be combinations of these.